In this video, we're going to talk about the effects of changing the units of measurement for either a dependent variable or an independent variable. Let's consider the case of a bivariate relationship between a dependent variable and a single independent variable. When you estimate this relationship, the units of measurement might be in terms of US dollars, and you might want to convert it to some foreign currency value. Or you might have units that are measured in terms of millions. That might be more convenient to express in terms of billions, and so forth. So here we're going to talk about what happens if we change the units of measurement. If we rescale either the dependent or the independent variable, we'll have a new variable as a dependent or a new independent variable, which will be some constant times the original variable. For example, if the original value was measured in terms of billions and the new variable is going to be expressed in terms of millions, the constant would be C1 or C2, depending on whether it's the dependent or the independent variable, would be 1,000, because there are 1,000 millions in 1 billion. Taking those relationships and substituting them into the original equation, we end up with a relationship in terms of the transform variables given by this, where the new variable y tilde is equal to a new constant term plus a new slope coefficient times the transform variable x plus a new error term. And what we see here is the new intercept is scaled by whatever factor we multiplied the original dependent variable by. So if, for example, we converted from measuring things in billions to measuring things in millions, the new intercept will be 1,000 times larger than the original one, because the new units are 1,000 times larger. So when we measure the intercept in terms of millions, that will be 1,000 times the intercept as measured in terms of billions of units. If we look at the impact on the estimated slope coefficient, we see the new slope coefficient will be equal to C1 over C2 times the original value. So if we rescale the dependent variable, the slope coefficient, remember, is a change in y over the change in x. And because now the new units of y are 1,000 times larger, then the change in y will be 1,000 times larger, and therefore the slope will be measured as 1,000 times larger. On the other hand, if we rescale the independent variable by 1,000, the impact of a 1-unit change would be 1,000th of the original change. And that's why we divide by C2 there. Notice, though, if we scale both the dependent and the independent variables by the same amount, the slope coefficient will be exactly the same. The error terms will be rescaled so that they change in the same proportion that the dependent variable was rescaled, because their error terms in terms of the deviation of the observed y from the predicted y. One thing we should note, though, is that hypothesis tests are unaffected by changes in the units of measurement. The reason for this is that both the numerator and the denominator of t ratios and f statistics will be rescaled in the same proportions. As a result, the t ratios and f statistics will remain exactly the same. One other thing we should talk about when we talk in terms of units of measurement is that in general, economic data is only reported out to a certain number of significant digits. Quite often there's only 2 or 3 digits to the right of the decimal place. In general, when you estimate relationships, if you have a variable that's measured only out to 4 significant digits, when you report your estimated coefficients, t ratios, and standard errors, you shouldn't report more accuracy there than there is in the underlying data. So there's no reason to report 10 or 11 significant digits for your estimated slope or intercept when the data is just not measured that precisely. In general, the number of significant digits you report when you report your regression results should be consistent with the level of accuracy that's in your underlying data.